So IntelliDrive makes this motor and packages it with this drive so that you don't have to do any setting and tuning and configuration. Well, maybe a little fine tuning. That's about it. You don't need to see all these tools that I had to use to mount this thing to my desk, so I'll just move this over here. So yeah, it's about 200 millimeters. I found IntelliDrive on the internet, and they do all kinds of applications, direct drive motors and whatnot, for various industries. So they have a good collection of drives and motors. I had to Google this motor, this PSR250, and you can see table diameter, 200 millimeters, height, aperture. I think we're in a delta configuration because the voltage is higher, for the bus voltage is higher for the back EMF to hit the speed. I see 45 newtons of continuous and 17 of peak and a 14 amp peak current. I'm using a drive today that does 12 amps, a Zenith compact, but that's pretty close. We won't lose much performance with that. I'm going to do no load testing. So let's take a look at the CME software. I'm going to connect the drive over the serial port with my RJ11 to USB adapter. This is a Copley SER-USB-RJ11, and we sell this now. It's got prolific drivers, so I installed my prolific drivers on Windows, and I can just get this thing hooked up here. So yeah, I'm connected over the serial port. It found the COM4 or COM port because there were drivers installed. Now I'm connected. So we're just going to run quickly through the basic setup. We're not really going to change much. Brushless rotary, that's good. It's incremental only. There's no Halls on this motor. There's options for absolute encoders and whatnot too, so that's fine. 409600 counts per rev, and there's an index on this. I'm going to use it for homing, so might as well use loss detection. Don't need to get any CRC fault. If I had a break or wanted to come to a controlled stop during an E-stop, I would set this stuff up here for how to come to a stop. Position mode, can open over EtherCAT. This is a Ethernet drive with EtherCAT. And multi-mode port normally just buffers out, but here's an interesting one. I can emulate the output, and then I can divide it down. So 4096,000 counts per rev is like 4 million counts per rev at 100 revs per second. So maybe I want to divide it down. So no need to change anything. So just the configuration that they give you, all configured with the CCX file. But we'll take a look at the motor spec. This is a 34 pole motor. I measured this inertia. It's a little bit more than what was indicated, 0.01. I measured about 0.02. Maybe my measurement's wrong. Peak and continuous, given a Newton meters per amp, that looks good. And if I had 250 volts or 240 volts AC rectified, which I could wire this up, maybe I could go 800 RPM. Just double checking the torque constant, Newton meters per amp, volt per radians per second. I measured the resistance at 3.5 ohm, and I measured the inductance at twice what I had earlier. So the calculated values, you don't have to use the calculated values, especially if somebody tuned it, because it would overwrite their tuning. But if you just were going from the motor data alone, and if it is correct, then the calculated values would do good. So I'm just going to check the various loops here. Current loop tuning. So I should get a band. Well, there's a phase init error. So it was phase initializing while I was trying to tune the current loop. So I just started it again. Current loop bandwidth should be about 1.2 kilohertz of current loop bandwidth. 1.3 is good. So the data looks really good. That's just from the math model. Take a quick peek at the velocity parameters. You can see with the correct value of inertia in here, I generated values which are not too stiff. And I have a speed limit. I probably won't be able to hit that because I've only got 120 volts AC today. But you can see there's some tracking windows and there's some gain values. We're just going to check the phasing real quick before we do any kind of movement. It is important that while you're rotating forward that the counts go up. So you can see here, if I set the 0 when I go forward, I'm going clockwise and the counts are going up. I like that. There's also a phase initialization current and force, so this will apply 10 amps to the inertia for a period of time and then ramp it back down and then wiggle it just to make sure. And there's other options in a limit switch or increment by 90 degrees. So if you have difficulty doing the phase initialization, this is why we should have halls, so we don't have to do the wake and wiggle, or an absolute encoder. But this is okay. It works as long as we all agree that it works, then everyone's happy. And so that's a little bit on phasing. Take a quick look at the P loop. We got some tracking window. We'll tighten that up later. I'm going to try to do some really fast moves today, but I'm going to have to tune this thing up. But just with the calculated values or the file that it comes as the package, I don't have to change anything if somebody sets up a package for you. So this is purely from the math model calculated values. It's not too bad. A little spongy. There's a little bit of a cog to this motor, and we'll take a look at that in a little bit. And maybe on the next video, we'll figure out how to get rid of that. But for now, looks pretty good. So I'm going to go through the process of manual tuning. We did the manual phasing. So now I'm going to do the manual tuning. So function generator tab, apply to current, auto setup checkbox, hit start, gains tab. So find a gain that's too high and cut it in half. That looks pretty good. And we'll try it. Trying to get too much integral. Yeah, see, little integral wind up, back down. That looks good. So even at an amp, this should still look okay. And of course, at the 5 amps. Yeah, there's a little slew rate limit there. Large inductance, only 120 volts AC rectified. That'll limit your bandwidth with larger amounts of current, but it's pretty good. Couple of milliseconds to get to that current, not bad. I guess if you're making a 20 millisecond move, slew rate limit would get in your way a little bit, knock off a few milliseconds, if that's important. So we'll take a look at the velocity loop now. You notice the motor didn't move. I bolted it to the table there. So the velocity parameters, I'm just going to knock this down a little bit. I don't want to do crazy acceleration while I'm trying to tune, but auto setup checkbox. Apply to the velocity loop. 40 RPM, 5 hertz, bang, bang, bang. That looks pretty good. We'll give it a shot. So it's wiggling back and forth. We're trying to get a nice trap waveform here. If the gains are too high, you will break into oscillations. Let's see what that sounds like. So if you double the gains and it breaks into oscillations, cut it in half. There's the oscillations from gain being too high. I will note that the default filter is 2-pole 200 hertz, and I don't like that. It's good for softness, but we're trying to push the limit here, so I'm going to make it a single pole for starters. I may come back and push that pole out for really fast moves, but you'll notice there's no oscillation now. So gain margin and phase margin, I'm going to take back some of my gain margin here and leave that alone. Trying to see if we can see too much integral. We'll definitely see that when we do the position moves. Yeah, there's a little too much integral windup, jumped above. So I still think that's a little too high for integral, and we'll see that in the position loop tuning. So current loop, about 1.2 kilohertz of current loop bandwidth, plus or minus a couple hundred hertz. That should be fine. This is a 34 pole motor, and that's 17 electrical cycles per second times 100 revs per second would be 1,700 cycles per second. So I could use a little bit higher current loop bandwidth if I'm trying to go 6,000 RPM, but maybe not. Maybe not with this motor, maybe not today. So this is a good current loop bandwidth. We know VP will oscillate if we crank it up too high. It could be a little susceptible where it is now. We do have some phase margin, maybe not so much gain margin. The integral may be too high. We'll come back and turn that down. But the default for PP and the feed forward, if you have a large inertia attached, there's no inertia here except for the motor's inertia. But you know, if there's like 50 pounds on here, you might want to knock a zero off of this and make it 100. But we'll leave it at 1,000 for PP. So I can do a single rev 496000, and this looks like good calculated values. Let's see if we can make this single rev move. Maybe that's too many zeros. That was 10 revs. There, 1 rev. So this will allow us to look at the gain of the, yeah, as you can see, a little too much integral wind up there at the end of the move. So we'll cut that down. Maybe a little bit too much still. The little S curve on there, round off the corners. You see the trajectory limits with S curve, rounds off the corners. Pretty good within 50, 20, well, within 10 counts, the end of the move. That's pretty good. Let's pause for a moment. So this is a 1/16 rev, 50 millisecond move. That's why I bolted it down. We'll take a look at the profile velocity. It's got some S curve just to round things off. Acceleration, I have to be careful because I'm already hitting the 12 amp limit on this drive, although I could go to 14 amps on this motor. It's not much different. So good acceleration, good decel. I could increase the trajectory to hit some limits, but I don't think this will help me. So that's a much faster 20 millisecond move. I'm hitting all kinds of peak limits. It's not really under control. Total move time 40 milliseconds. Trajectory done in about 20 milliseconds. To get to the 20 millisecond mark, I'd have to really increase the acceleration on this and maybe some velocity too. So this should be, yeah, about a 20 millisecond trajectory command. Yet I'm current limited for peak and acceleration. There's a lot of bouncing going on. But I did pretty good within a couple hundred counts at the end of the move there.